Hi, I welcome you all for this session. In this session, we are going to discuss ARM7 based LPC 2148 general purpose input and output ports. So let us first understand the pin configurations available in that LPC 2148. So total pins in LPC 2148 are 64. You can see in this diagram, it starts from 1 to 1 and it ends at 64. Out of which 45 pins are used as general purpose input output pins. How these 45 pins are designated to ports. LPC 2148 has two ports, port 0 and port 1. For port 0, the 29 pins are allocated, and for port 1, 16 pins are allocated. So please note it down. For port 0, 29 pins, port 0, 29 pins, and port 1, 16 pins. So totally you will have 45 pins. If you see this diagram, almost all pins have multiple functionality. That is, this is the primary function of the pin, default function. So PO represents port 0 and .21 represents 21st pin. Here PO represents port 0 and .22 represents 22nd pin. So these are the first options are the primary function. It can access GPIO, input or output port, general purpose input output port. And the secondary options are this pin, 21st pin, can act as the generation of pulse width modulation signals, and it also can act as A to D converter, and it can also be act as capture timing signals. So how it can be accessed? Default operations primary function is it should act as input and output operation. It has to do, right? Data has to get into the processor, or data has to go out from the processor. But I want to use this pin, 21st pin, as to generate PWM signal, pulse width modulation signal. Then I have to choose this secondary operation, and this is the secondary operation. This is the first secondary operation, and this is the secondary, and this one is the third secondary operations. Okay, here comes the question, how I have to choose the secondary operations. There is one register called pin select. In the pin select register, if we give value, okay, for secondary function, there is a designated value. For the first secondary function, designated value. Second secondary function, there is another value like 10, 01, 11, right? Like this, you can select the secondary functions. Suppose 10 represents PWM. If you want to generate PWM, then you have to put in that register, pin select register, as 10. Then that pin will act as PWM timing, PWM signal generator, right? So like this, 01 for analog to digital and 11 for CAP. Actually, each pin can have maximum 4 functionalities. That's it. Okay. So from this slide, we can understand that the LPC2148 has 64 pins. Port 0 contains 29 pins and port 1 contains 16 pins. So totally 45 pins or GPIO pins. And what about the remaining pins? We will see in the next slide. Okay, now coming to the registers section, ARM has 37 registers, each of 32-bit long instructions. Each can handle 32-bit long instructions, each registers. And we have one program counter to locate the next instruction, address of the next instruction, and one current program status register, CPSR, very, very important. It will tell the mode of operation. This is mainly to tell the processor about the mode of operation. We will discuss in the coming slides what is the mode of operations like and its concept. And next one is saved processor status register, SPSR5, and GPIO processors 30. We have 30 registers. Okay, so totally ARM has 37 registers which can handle 32-bit long instructions. See here, this is the mode of operations. There are 6 types of mode of operations. 6 types: user and system mode of operation, fast interrupt request mode of operations, interrupt request mode of operations, supervisor operation, undefined operation, abort operation. So in this mode of operations, user can go only with this mode of the first type only the user can handle. That is, the user can get registers R0, R0, R1, R2, R3, R4, R5, R6, R7, R8, R9, R10, R11 and 12, and 13 for stack pointer. This is for stack pointer. This is represents stack pointer. And this is R15 for program counter, which points the next instruction to be executed. And this R14 for linked register. Linked register. Okay. So what is the need for linked register? This register is mainly used in branch loop operation. Branch loop operation. Suppose the processor is doing some computation. Suddenly, an interrupt disturbs the normal flow of operation. Now, the processor has to give priority for the interrupt. What it will do? It will give this. It will branch. It will come out of the loop, and it executes the interrupt operation, and it has to go back to the main function. Go back to the loop to continue its normal operation. So whenever it comes out of that loop operation, that address, branch address or loop address will be stored in this linked register, so that after execution of this interrupt or subroutine, it can come back to this main function on referring to this linked register address. So linked register is mainly to make the program execution get back into the main loop once the subroutine or the interrupt operations are completed. Okay, so for this mode of operation, in the user and system operations, these registers are available, and along with one CPSR. As we see in the last slide, one CPSR is available, and 5 SPSR are available. So this is the normal operation flow. Suppose the administrator want to check some registers, he has to switch over to supervisor mode. So he will transfer the CPSR register details to SPSR. So this is saved. So all the things what are available in the CPSR will be saved in this SPSR register. And once the supervisor completes, the administrator completes his checking and everything, hardware checking or software checking. Once he complete, he can switch over back to supervisor mode, from supervisor mode to normal user mode. So that time this SPSR will give back all the details to CPSR once again. CPSR, which it got from long from CPSR when it switched from user to supervisor mode. Okay, so SPSR will maintain the content of the CPSR, so that if the mode supervisor mode go back to the user mode, the CPSR should have the original data value, so that it can continue its normal flow of operation, right? Okay, the registers which are available, this from R0 to R7 is available with FI fast interrupt request also, and up to from R0 to R12 is available to interrupt request. The same registers can be available supervisor mode also. Okay, the next slide will give you the detailed programmer's model. See here, in the user system R0 to R14 and PC CPSR is available, right? And supervisor mode R0 to R12 and R13, R14 for supervisor mode. Program counter is also available. And abort mode also R13, R14 for abort mode of operation. PC is available. General purpose registers are also available from R0 to R12. This is undefined. If there is any error exceptions, the mode of operation will change to undefined model. And if there is any interrupt request is received by ARM processor, then it switch over to this interrupt mode of operation, wherein all these R0 to R0 to R12 registers are available. R13, R4, R13 and R14 for allotted to special interrupt request handling registers. And this same thing is for fast interrupt also, wherein R0 to R7 are used as general purpose GPIOs, and R8 to R14 is mainly allocated for fast interrupt mode of operation. And PC is available, program counter is available. Okay, see here, CPSR is available for all this model of operation, and SPSR to save the CPSR is also available. So this is what I discussed in previous slide. This is very important, this program status register. It is a 32-bit register. The LSB, this will gives the mode of operation. Mode of operation, it is given here. See here. If it is 1000, so 10000, then normal mode of operation, user or system mode of operation, user mode of operation. If all ones means that is system operations. And if supervisor operation means 10011 means supervisor mode of operations, right? And this IFT, interrupt disable bits. So if it is 1 means normal flow is going on, normal operation is going on. If it is 0 means then the normal flow, the user flow should be shifted to interrupt flow. Shifted to interrupt flow, then it becomes 0. Instead of 1, it becomes 0, and then 1 0 0, it becomes 1 0, because normal flow is shifted to interrupt request flow. This normal is shifted to interrupt request flow. So while shifting, it has to convert this 1 to 0 and 1 0 0 4 0 zeros to 1 0 0 1 1. For interrupt means 1 0 0 1 0. So in this way, this CPSR register will maintain the value. Okay. So the maintained value will also be transferred to saved status register. And see here in the MSB section, you will have condition code flags. N represents negative flag and Z represents zero flag, C represents carry flag, and overflow flag, B represents overflow flag. So depends on condition, the operation will be executed. Suppose you are adding, carry is set, then C is equal to 1. If you are subtracting same two value, if you are subtracting 1010, what will happen? Everything will become 0. Right? Or if you do XOR operation, everything will become 0. The result of the data is all same. That is, all are 0. Then 0 flag will be set. It will be set as 1. Right? So this program state register is very important because it maintains all the values, the condition code also, flags also. And see here, this is T bit. T0, that is the ARM state. If T is equal to 1, that is in thumb state. That is 16-bit or 8-bit instructions are executed in thumb state mode. It has separate set of instructions available for thumb state, and ARM state normal set of instructions. What we are doing in our lab now, that all related to ARM state instructions only. Okay, so please remember, from 0 to 4, 5 bits for mode of operations, and I and F for interrupt request, fast interrupt request, and T is for thumb state or normal mode, and the last MSB, last 4 MSB is for condition flags. I'm going to end this session. Thank you. We will meet in the next topic. Thank you.